Hello guys, and welcome to the ultimate video tutorial to grade your first CFD solver. Personally, I think following along video tutorials is a great way to learn. It captures a lot of the nuances that it's impossible to capture in gritty materials. This is, however, like the fifth time that I try to get past the first 5 minutes. So there's a disclaimer: if I run into trouble, that's going to be expected, and I also hope that's also valuable, because I think looking at someone live coding, it's valuable because they also usually have to solve problems on the go. Sort of like you have to listen to their thought process. So I'm going to try to talk out loud as much as possible, even if there's not always as much clarity as you would usually be able to find in gritty material, such as the one that we're actually going to be providing, which is here, the ultimate guide to grade your first CFD solver. This is the in-house implementation, which in turn is based on the main sources of references that we're going to be using. You're already familiar with the paper by Owkes, 2020, a guide to grading your first CFD solver. This one is important. Take your time to understand sort of like what it says, especially section 3. We're also going to be looking at the resource by Professor Lorena Barba et al. 2012, 12 steps to Navier-Stokes. In last class, we introduced the two-dimensional Poisson equation. We're going to be looking at the step 11 of their guide this time, cavity flow with Navier-Stokes. All right. There are a few differences that I think it's important to emphasize between the approach by Owkes and the approach by Professor Lorena Barba. Our guide combines their two approaches in important ways. You should take a look at section 3 of Owkes' Temporal discretization. He talks about the Predictor step and the Corrector step. If you take a look at our in-house implementation, you're going to realize that to use a Predictor step and a Corrector step, Professor Lorena Barba does not do that. And the reason is, we might say, they think of the pressure Poisson equation differently. There's a video in the readings in which Professor Lorena Barba derives this pressure Poisson equation in this way. We're going to be attaching a short screencast in the reading soon, in which we derive the pressure Poisson equation in this way. Owkes uses the pressure Poisson equation defined in terms of the start velocity. This U star is nothing more than the velocity without the influence of the pressure. In a way, that's what the Predictor step is. It's the velocity. It's computing the velocity without the influence of the pressure. We talk about that in our guide here. We try to put it that way. Where is that? Here, yeah. The Predictor step is nothing more than the value of the velocity without the influence of the pressure. Make sure you take a look at these comments. So, in that sense, our in-house implementation is very similar to the implementation by Owkes. You know, section 9, general overview of the code. We have the Predictor step. We solve the Poisson equation, and then we have the Corrector step. This is what you got here. perhaps even slightly more simplified. That's intentional. Because we also take a lot from Professor Lorena Barba's implementation. In fact, we thought their implementation was amazing in terms of how they took advantage of vectorized Numpy operations. A vectorized operation is sort of like, they don't use for loops inside this for loop, because this is the for loop of the simulation, obviously, NT. But they don't have to iterate like twice, to put it that way, through the grid, They don't use double for loops. If you take a look at Owkes, he usually has these double for loops because he's not using vectorized operations. Professor Lorena Barba uses vectorized operations, so she doesn't need for loops anywhere. That is arguably cleaner code in many ways, but most importantly, it's faster code. Vectorized operations are known to be always faster in all popular programming languages, and Python and Numpy are not an exception. Vectorized operations are good. Having said that, Professor Lorena Barba's code we thought is a little cumbersome in terms of not reusing code a lot. So we also have functions in our guide. For that here, these were really nice. We thought this would be valuable to code things up this way, such that we can use these guys here, which leads to cleaner code. Sometimes it's necessary to sort of like refer to the whole grid, but whenever we can, we try to use the reusable functions, right? That's just good software engineering. So that's one difference. You're going to realize that our in-house implementation is really like combining both approaches, and in more ways actually. If you take a look at section 2 of Owkes, Computational Mesh, he does something that I cannot disagree with. There are advantages to his approach. Then I really think they come at pedagogical cost, and we talk about that here. Owkes uses a staggered grid to store the variables, where the pressure is stored at the cell center, and the velocities are stored at the cell faces, which is sort of like an odd choice. This is what you see in the figures by Owkes. We opinionatedly and strongly disagree with this. We believe this to be the wrong way of thinking about the problem, at least pedagogically, for first-timers. We prefer to think just of a mesh as a net of points. In other words, we do not distinguish between the border of a cell and its center, because we're thinking of a net of points. So we're just thinking of the center of a cell. We're not so crazy. Professor Lorena Barba does the same. So in a way, we're using the simplifying assumptions of Professor Lorena Barba's resource. In that sense, we're using this resource, the assumptions of this resource, right? But the predictor step and the corrector step stuff, that's all from Owkes. That's all from Owkes, section 3. Temporal discretization, all right? And the Poisson equation, as I explained, we also solve it sort of like in part how Owkes does it, but also we took inspiration of this formula. You know how Professor Lorena Barba discretized the Laplacian of the pressure, this guy, to arrive at this formula. This is how we solve the pressure Poisson equation. So in this sense, this is how Professor Lorena Barba does it, but the source term B is like the source term in Owkes, because we're using the predictor and corrector step. So our Poisson equation is, oh sorry, this one. This is the source term of the pressure Poisson equation. Our source term is like this. Let B be this guy, right? We talk about that here. It's truly a hybrid of both approaches. Owkes does this to solve the pressure Poisson equation. We don't do this, right? We don't set up things this way, but we set up things this way, but with a different source term taken from here. Best advice, familiarize yourself with this paper, this approach, and then take a look at this approach. Read the comments closely. Right. Okay, so that's 11 minutes of an overview of the three papers, which is important. Might seem like a lot of time, but I think it's important to familiarize yourself with these three resources before you make the most of this guide and the video tutorial. I'm going to try to code a few things differently, just sort of like to produce an implementation, and even new implementation here. You know, whenever possible, I think it's valuable to appreciate how a lot of things always can be done differently, depending on your preferences or any other arbitrary decision. Yeah, I think we're ready to go. Overview of the code. This is going to be useful. Last but not least, before we get started, make sure you use many power, use it with caution though, and activate both Corgi and Kitty mode. Alright? Okay, so first things first, what are we supposed to do if we want to call a CFD solver, your first CFD solver? Last class we worked on pseudocodes, which was very useful. I remember that the first thing that we are supposed to do is to initialize a few important things, such as the input parameters, the viscosity, the density, the number of grid points, time information, the boundary conditions, all of that stuff, the data structures. Right? So yeah, import your favorite libraries, right? Import Numpy as np. Import your favorite libraries. Wow, that might be too much power. Sorry about that. Actually, don't use that much power. Some power. Okay. Yeah. Import Numpy as np. I can't think of any other library that we need right now, so let's just choose that guy. What else do we need? I like to think in terms of the continuous domain, you know, continuous domain. It's min 0, it's max 2. this means the continuous domain, the maximum value of x as in your domain. You know, what's the domain of x? And the domain, right, what's the start of the domain of x and the end of the domain of x. Same with y. Now, this is different than the discretization, you know? Nx can be 41. Ny can be 41, all right? Now, what should be dx? Dx should be, you know, you take the difference, right? The difference in the start, between the end and the start of the domain, and you divide that by nx minus 1. I think this is relatively straightforward. Like if you want to divide your grid in 5, you need squares or divisions of 4 divisions, right? No, 5. Oh, this is why it's important. This is what I mean by live coding. Yeah, right, like what's the thought process here? If you want to divide, so 41 minus 1 is going to result in 40 divisions, right? Yeah, that's what you want, 40 divisions. 41 is like, where is it minus 1? Huh. I always know this, but so like forget. Oh, this is embarrassing. Probably you don't need an explanation for this, but so need to take a look at the grid. So here we have like 6 cells. I'm guessing this is n equal to 7. So if you want to determine the width of these guys, that's going to be the complete length divided by 6. Yeah. Yeah, because, well, it's not the right way to think about it actually. It might seem simple, but what is saying here? N is actually how many points you're going to have. Not really. One, two, three, four. Well, I might need to cut this, I think. Wish had a whiteboard. That's max, that's mean. Do we really need that -1 there? What's the point of that -1? Huh. I think the best way to explain it, I'm sorry for taking so much time, something so simple. 41 mesh points, you know? I really like to think in terms of points. 41 mesh points. Means 40 divisions. Right, because there are like 40 spaces between the 41 points. Oh my god, it's just that. Yeah, so you want to have the size of that, well, the whole distance divided by 40, obviously. Oh my god, there I go, back to kindergarten. Okay, yeah, sorry, yeah, dy. So you do need that -1 over there to actually keep things, you know, like true to their meaning. I guess you could technically get rid of it and your code would perhaps still work, but you know, the meaning of n would be slightly different unless you actually do this. Let's get rid of this underscore. Okay. Yeah. For one mesh point, 40 divisions, and it's n mesh points, n-1 divisions between those mesh points. You want the distance, the whole distance divided by that n-1. Perfect. So far so good. What else do we need? It sounds like we're ready to even create our data structures. Right. Velocity. np zeros, I think we can do here. Doesn't matter too much for now. np zeros, ny, x, b, np zeros, ny, x. The pressure, same thing. np zeros, and y and x. What else do we need? We need the viscosity, can be 0.1, I think, for example. Rho .001 or trying to remember. dt can be set up arbitrarily. At least that's how Professor Barba does it, so we're going to do that. It should be actually 0.001. I'll take a look at our guide, how we did it here. Yeah. Oh, rho can be. Oh, yeah, density of 1. You know, like, that's reasonable. But for the density, perhaps -1 would be too low. So our density of 1, is that the density of water? probably later, but okay, it doesn't matter. Okay, yeah. NT is really like the number of time steps, right? We don't need it for now, but let's reuse that. Why do we need these guys? We actually don't need them right away. It's not very apparent why we need those values. As a matter of fact, I really want to see why we need them at all. Huh, that's interesting. You see, this is why troubleshooting can be important. I kind of think, guys, that if we take a closer look, oh yeah, you only need this for the mesh grid. No, as a matter of fact, you don't need this. If this is confusing to you at first, why we need this stuff? Truth is, you don't need it. Just need for the visualization. Like if you comment this out, you don't need it right away. As a matter of fact, I want to be really minimalist with our implementation here. So I can comment this out because this NT, I'm sure it's a parameter that I'm just using here, like, you know, hard coding it here. This should be NT, but whatever, I'm hard coding it here because this is the NT. It's a parameter that's been taken from here. So I'm sure this is going to work because, well, code it up. Powers of the author, not really, it's nothing that hard. Really, this is all you need, actually, as you see, to set up your data structure. The global variables, the parameters of the mathematical model, and the data structures. That's about it. You know? Discretization variables, right? Well, continuous domain, as I like to call it. Discretization stuff, mesh points, global parameters, density, viscosity, and data structures. Right. Well, that took us a short while, but it's going to be faster from here. Now the boundary conditions. How do we set up the boundary conditions? There are two ways to think about boundary conditions: Dirichlet or fixed boundary conditions. We'll also talk about that here. Dirichlet boundary conditions, which are just actually defining the boundary conditions. Neumann or second type boundary conditions, which is defining the rate of change, at the boundaries, the rate of change of the function at the boundaries. We are using the cavity flow problem. The cavity flow problem is really a very famous test case. You can read more about it here. It's sort of like quintessential test case for numerical methods in computational fluid dynamics. That's why Owkes talks about it here. You may remember that towards data science reading that we also introduced a few class sessions before. This guy also uses like the same test case from the same paper. I want to show that. Wow, this is taking time to load. So this paper by Guy et al. Oops, they were, well, this paper by Guy et al. Right. Quintessential paper apparently for the cavity lead-driven cavity flow problem. But we're taking our boundary conditions from Barba et al. So here, what is this even saying? I guess I could copy and paste this, but I want to explain the concept. So bear with me. Here's the cavity flow problem. There's some sort of cavity. What is a cavity at all? Oh well, that's not what I was wanted to show. Cavity flow. Well, this is a cavity, you know? The first time that I heard cavity, I'm not sure if it's because I'm not a native English speaker, but I was like, okay, sure. But what's a cavity? A cavity is this sort of a structure. We're thinking of it like in 2D mode. So you can think of a very thin cavity, right? You know, like very, like no depth into this image. I guess this is how we should think about it. This is our setup. Like I built these walls. This is the left wall, the bottom wall, the right wall, and there's no depth because it's an idealized scenario, or it's super thin. Who knows? 1 millimeter of water. It's super thin. Right? The depth into the image is close to 0, or it's negligible. You know, there's no depth. This is a 2D problem. So we have the water here, the internal flow. According to the conditions of the problem, there's no velocity on either of the walls, right? And that kind of makes sense if you think about it. These are walls, so the starting point in the beginning, there's no velocity, but there seems to be some sort of external flow, right? Like, well, I don't want to call it external flow. There seems to be at the top certain velocity. Maybe it's because there's air at the top, you know, like the air has some sort of friction with the top of the fluid, and sort of like that starts some sort of like movement at the top of the fluid, because according to the conditions of the problem, the component U, which I think we all agree is like the horizontal component, has a value, big U. You could have been more creative than this. But that guy has a value. That's why the top, right? Boundary condition, U top. Owkes overcomplicates this because of the way he set up things, but really the top boundary condition has a value, 1, which is what you see here, right? The horizontal component of the velocity in the top boundary condition has a value. Positive value gets towards the right. If we want to think about it that way. And that's going to start an internal flow that sort of like maybe ends up looking like this, which is sort of like what we see ends up happening, right? You know, I think that matters, you know. So if someone tells you those are the boundary conditions, that's all you need to know to start coding this up. So let's code it up. Boundary conditions. Each letter fits the boundary conditions. Let's start with the top because, you know, that's the first thing that comes to mind. What's the top? Well, in like the first, if I'm not mistaken, NumPy arrays work like this. The first index is the rows. Now this is somewhat confusing because when I think of rows, I think horizontal, right? Rows are horizontal. However, if you are actually counting rows, you are thinking, like from top to bottom or from bottom to the top. So you are thinking vertically. You might think that the first guy is the J index and the second guy is the I index. Or you may even think that the first guy is like the Y dimension and the second guy is the X dimension. But perhaps the best way to think about it is like the first guy is the M row and the second guy is the N column. Because when you think of matrix math n by n, the standard, and this is the reason really, the standard is that mathematically, when people think of matrices in math, in linear algebra, they think of m rows and n columns. M by n, and people say m by n. They don't say m by n. M by m. They say m rows by n columns matrix. This is why NumPy does it this way, and this is why Professor Lorena Barba follows that standard. And so when she's thinking of the top boundary condition, like she's still thinking of everything the same way, just like she accessed the x coordinates in the first index. No, wait, the y coordinates in the first index and the x coordinates in the second index. I know it's confusing, but you just gotta keep that in mind. When you think of NumPy matrix, think of this. Weld this up, always. Very useful. You can say thank you to me. What are they? Okay, so if we are thinking of utop, then that's this is a Pythonic way to do it, obviously. At the same time, -1, right? Like the top, but -1. Hope that's correct, right? I might need to double check because I'm wondering if the 0th row starts here. No, I don't think so. Huh, that's a good question. Huh. Well, let's actually test it out, right? Print u. How are we thinking about this? We see it at the bottom. Yeah, this is because obviously the first row is the first one, right? So I wonder if utop is actually, but obviously this is just, I guess this is the idea of the mesh grid, right? Like when we say that np linspace it's min, it's max, and x, right? When people do this, np.meshgrid, this is because they want to Yeah, that confused me. I guess we also need to explain this later. what meshgrid even means. It also confuses the hell out of me sometimes. Let's make sure. Yeah, utop is -1. You know, this is just a convention, you know, like, because don't print this, guys. It's going to confuse you more. Like, because we're thinking this out, like, in terms of well, U0 U0 U0, huh, this is funny. Almost seems like it could have not possibly coded this up. I counted it. How are we thinking about it? Forward is usually like towards the positive, right? Absolutely. Yeah, I think this is correct. I mean, I think it's symmetrical anyways, but this is the top. Everything else is the bottom. How can I convey that to you, though? I'm not sure if I'm conveying it in the best possible way. Perhaps if we visualize it, I want to convey that to you more effectively. We won't give up. Not yet. I think I can convey that to you. Perhaps we can visualize something just quickly, whatever, like really anything. Yeah, right. If we, this is the perfect way. Maybe strolling, lively, embarrassingly. It's worth it. Take a look at this. Right. This is our implementation. Visualization setup. Right. This is the utop boundary condition. So what's going to happen here? We should see the value of the contour being higher at the top, unless I'm mistaken. Well, we need also matplot imports numpy as oh wait, what am I saying? Matplot div multiply-plot splt. I think we also need another. We also need this CM thing. Oops. From matplot import pyplot splt and CM. Right. Yeah, you see? Well, I guess there's a better way to show this. We need, well, we have the contour, the color bar maybe. You see, this is 1.01, what the heck. It's 1 really. This is 1, utop, you know? You see? Utop is 1. Utop can be 100. So don't print this because it's going to confuse you because of the way this is set up. Like it's because it's an array of arrays in the end of the day. Like obviously this prints up this way because this is an array of arrays, and this just prints the first array. But when you're thinking about this mathematically, not programmatically, the first array of the matrix, we like to think that guy is here, right? So that's really funny because if you think about it, Numpy uses notation from a standard math notation, but this is actually reversed, kind of. Well, I guess the matrix is like this in Numpy. This is the matrix in Numpy, but when we think of a matrix to represent this domain, we just think of it like as we usually think, right? The mapping is the right mapping, the correct mapping, right? You know, the largest values, you know, length of, well, the largest values, right? Like, you know, like the 40th value in this case, right? Is the last guy, the top guy, right? And the smallest values are the smallest guys, right? Let's initialize this again. Right? We can change it to the bottom. Right? Yeah. The first row, the 0th row, the bottom row, right? The small values from all. So in that way, you just think of it very similarly. I hope this was insightful. I learned a lot right now. I hope you also learn a lot. And I implemented this like for a lot of days. But it was very useful. Okay? Wow, I really like this. We're going to... Well, I guess we might need it for later. Might need it for later. I don't know, that code was nice. I think this was really useful. To sort of like make sense of it. Okay, so that's how we set up boundary conditions, right? You know, in this case, you know, just to emphasize this, we're going to do this differently. We're going to say ny minus 1, you know, just to emphasize this. We could obviously do it like we did it here. But just to emphasize the point, we're going to do it like this. U top is this guy. U bottom is nothing more than this guy. Zero, 0th row, all columns. Right. Now, the u velocity is the horizontal velocity. That obviously is like, you know, you gotta set it up like 4 sides, right? So it's like you just need to set up so right, u right, and u left. Obviously the same with the b's, b top, b bottom, b right, b left. I really hope my screencast is not going to like just cut off and not saved for whatever reason right now. That was short. But okay, so you're right, that should be all rows, you know, farthest column. Oops, what I'm doing here. Yeah. All rows, first the zeroth column, right? Perfect. And I guess just sort of like can oops, that's what I'm doing. Well, probably should have just written it to emphasize again, but well, no need to take that much time. The V component, that guy is 0. Oh well, this is actually 1, right? Anyways. Okay, these are boundary conditions. Oops. Right. Now we also want pressure boundary conditions. Those are a little more involved here. We still don't need to think about the pressure yet. So I'm just going to leave that cell here, pressure boundary conditions. Let's try to live in a world without pressure. Okay. These are going to be Neumann boundary conditions. Well, they don't talk about the pressure here, but these are the boundary conditions for the pressure. I guess I could just copy and paste, but we'll need them later, so we are going to copy and paste that later. The discretization of the domain. This is really nothing out of the world. Approximate derivatives with finite differences. I guess we could do something like pause the video and call this up before we come back. Yeah, try to do that. Pause the video and call this up before we come back. Just like, you know, like make sense of it, right? I mean, obviously you're already looking at this, but like, stop taking a look at this and call this up, right? You know, like discretization formulas, like we're going to need them. Alright, I hope you paused the video. You know, really these discretization formulas, where does that come from, like at all, right? Well, it's just the finite differences approximations that you're already familiar with, I hope. These guys, you know? These are very useful. I took inspiration from Owkes in a way, like, I thought, okay, these are like the finite differences that I need, so I'm going to use the usual formulas. We're going to need these kind of guys, right? So we call this up. Now what is funny is that Owkes needs to do this weird thing here in equation 11 and also in equation 15. He needs to do this mess because he's set up things in a weird way, a cumbersome way. You don't need to take a look at this. We're doing things like Professor Lorena Barba's, you know, like as we already explained before. Now, Professor Lorena Professor Lorena Barba, she's using forward differences. Owkes is using center differences, you know, for the first order derivatives, first order finite approximations. Owkes is using center differences, but Professor Lorena Barba uses forward differences for those approximations. And I feel that the reason might be is that the code is already too big, you know, like look at this code, this is just like too cumbersome. very unreadable if you ask me. So perhaps for pedagogical purposes they used forward differences, but I don't think that's really very necessary, like, because center differences are better, right? Obviously second differences are in a way already center differences if you actually take time to derive them, but the first differences you can have, first order differences, you can have either forward differences or backward differences or center differences. In our implementation, the in-house implementation, we're using center differences for the first order differences. But let's use forward differences, right? Why not? Just in this tutorial. So define forward diff first. Well, a forward difference is like a first difference anyways, first order difference. This should take a function. I guess it can take the x, but let's do things differently, right? So let's assume the x is a global variable, right? Why not? I like to play with things differently. So we have our grid, right? A forward difference, right? But we exclude the boundaries, right? We don't want to get out of the boundaries. So how do we do this, right? Well, the guy in town is just jx, well, ji, right? J plus 1 I, right? But obviously this is not how you are coding this up. You want all j's and i's, not just one particular ji. So you want the entire grid, actually, right? So you want the entire grid. What's the entire grid? Well, the entire grid is just f, but you don't want the boundaries. Those are the boundary conditions. So you just want everything that is in between, everything that is between the first row, which is actually a 0 row, but you don't want that one, so you say that one, and the last row, but you don't want that one either, so it's like -2. But thanks God for Python, we can -1. This is actually a Pythonic way to do it, but it's sort of an abuse in a way of syntax. Not all programming languages have that. So, well, same here, right? But, move these forward, right? But not this guy, because this guy is the vertical direction, to put it away. So it's really here, we're dealing with x. So we're going to say 1 forward. Well, 1 plus 1 is 2, minus 1 plus 1 is 0. But, although this is technically correct, I think it's going to freak out, because it's going to think that it's going to, like, from 2 to 0, right? But obviously you just want to say go to the end. That's what you actually want to say. Right. In case you were wondering, this operator, this semicolon, these 2 dots here, this obviously says like until -1 or less, right? That's what it says, right? It does not include the -1, so this is why this works, to say everything that comes before the last guy, right? Really, now you say include the last guy, because actually -1 is the last guy, but it's not inclusive, so that's why usually when you say -1, it's like everything before that guy but starting from this guy, you know? Right, like it says start from this guy, but everything before this guy. This is what this operator says, in case you were wondering. Yeah, it's like a for loop, non-inclusive till the end, right? Till the end, non-inclusive, keep it away. Okay, so I hope that was not more confusing than it already was. Forward if y, same thing. Term f. What are you doing here? Well, right? dy, yeah. You know, this is the formula for the second difference, right? I hope you're familiar with it, right? Like this is the formula for the second difference. Nothing else is world. Straight out from here. But I'm going to do something very daring, you know? Let's experiment. I'm going to... What's a forward difference if you think about it? What's a second order difference if you're thinking about it? Like, a second order difference is an approximation of a second derivative, right? But what's a second derivative? It's a rate of change of a rate of change, right? Oh wait, I was going to say that it's also like the forward difference minus the backward difference. Can I say that? Is that correct? The next difference and the one where I'm at. Forward difference, backward difference. Yeah, you know, technically, like, there are many ways to derive the formula for the second difference. Like, you can say the forward difference, like, that comes... Well, no, it's actually that, right? It's the forward difference minus backward difference, because second order difference, like if you take a look at like a... Well, I wish I had a whiteboard just to show you. But you know, it's a rate of change of a rate of change, right? So it's how the rate of change is changing across every discretized distance, right? So if we say backward difference, right? You know, we start from here. But we go backwards. Wait, can I do this? Hope this is fine. Yeah, I think this is correct, right? Like go one backwards. So same here. Bear with me. This is obviously different than how we implemented it in the guide. Yeah. So that's true. Yeah, this is a backward difference. And why? So if we say we want to implement now the center differences, should be able to do that, you know. It's like, well, what's the name? Diff second x, right? Diff second x is going to be, I'm going to say, It's the forward difference in f minus, it's the rate of change of the rate of change. That's what we gotta think about. It's the rate of change of the rate of change. So this is our rate of change. Yeah, the rate of change of the rate of change. Yeah, it's like the rate of change of a different function, right? The derivative is a function in a way, right? It's the rate of change of a different function, right? We just say that. Right. Why? There's probably a better way to code this up, like, you know, with parameters and all, because like I'm obviously burning code out here. So maybe you want to actually use only 3 functions here, right? Like a parameter, like some sort of like diets type of thing, and you can have like an if here, you know? If diets, use diets, right? I guess that's a better way to do it. Arguably, you know, might be a better programming engineering practice. You might want to actually try to do it that way and adapt the code. That would be a worthwhile way to play around with the code. All right, so yeah, we have here our discretization to our formula. That should work pretty well. I'm not sure if this is more computation efficient though. Since I warning, probably not more computation efficient. But it should work. It's pedagogically interesting. Obviously, this might not be more computationally efficient because you actually have to do this like operation more times. You know, if you think about it, like, I feel like you have to do divisions, which are also costly, supposedly. And yeah, but you know, it should work, and I think it's pedagogically interesting, which is sort of like the most important at this stage. Alright, what do we even do next? Let's not take a look at our paper. Let's take a look at Owkes. What would you like to do at all, if you think about it? Well, you have the discretizations, you have the data structures. So why don't you just go and get the velocities, the next velocities? If the pressure is a problem, get them without the influence of the pressure. That's what we're going to do, actually. Really. You know? Because we start with this mathematical model. Let's take a look at this. This is our mathematical model. The balance of momentum equation, the conservation of momentum, this guy, the big guy, and the conservation of mass. We're thinking in terms of time, right? We have our mathematical model and we want to predict what's going to happen. So we're thinking in terms of time. So why don't we move this guy to the right side? So that we end up with something similar to this, to put it that way. And then we discretized the time derivative, partial derivative of the velocity. This guy, right? You know, this is very easy to discretize, nothing out of this world. A forward difference, in fact. Here you obviously want to use a forward difference because it's how you are going to model, you know, like going to the next step, right, from the current step. Here it's very useful to have like a forward difference, which is what you're seeing here. But it's really how we're modeling, how we step into the future from the present. Because that's what we do. From this guy, can go to this guy. You know, the first time that I did this, I hesitated. I was like, can I do this? Yeah, you can. You know, this is a valid formula. So if this is true, oops. If this guy is true, then this guy must be true, right? The next velocity is equal to this whole thing times t times the velocity at the, plus the velocity at the present. Yeah? if you have this, you have everything you need. Except for the fact that we don't have the next pressure, right? Why do we want the next pressure? Well, in session 8, we solved that question, I remember. We answered that the main reason is that we're enforcing the idea of the conservation of mass. You know, you cannot talk about conservation of mass if you're not thinking that the next velocity must satisfy the conservation of mass, right? So its relationship with the pressure must satisfy the conservation of mass in one shape or another. It's sort of like that. Do not bother, just assume you need the next pressure, not the current pressure, to put it that way. But you don't have that guy. So this formula is super useful, except we don't have this guy. Nevertheless, this is how it would break down. And, you know, technically speaking, this is how you would code it up. So, sort of like, this is what you would follow in the code, this discretization, right? You know, you already have the formulas implemented for these guys. I like to think of them that way, you know. Don't break this down further, like here, because it's already abstracted away here, right? Assume you have functions in your code to approximate these terms, right? Because you do. So only by taking a look at this, we could produce a function. Really. But truth be told, because we don't have the pressure, we're going to forget about the pressure. But other than that, we have everything to call this up, except for the pressure. So we're going to call this up, but avoiding the pressure, right? So everything else except the pressure, but based on this formula. We're going to call that the predictor step. I won't tell you why yet, but probably now, but I won't tell you yet. No, you know, let's not call it the predictor step. Velocity without the influence of the pressure, because I don't know that yet. Right? I mean, that's why. You know, that's what we're doing here. You know, predictor step is a fancy word for this. We're just calling this up. Def del without pressure. Because, you know, that's what it is, really. You know? Yeah, you know, it takes U, it takes V. Yeah, it takes U, it takes V, and it takes that, just that, really. I guess it takes dt and other things, dx, dy, but these are really global variables. I know in this guy we coded it differently, but that was not necessary technically, so we're sort of like on the go changing things, because that's also a great way to learn. So the velocity without pressure only takes u and v, you know, if you think about it. Well, there are some nuances here in our implementation, vectorized implementation. Un, we're going to say it's u copy. Thank God for Numpy. We can just copy things with a function, v.copy. Copy, what? Copy. Right. Oops, the end, right. And we're going to say v, but not all of v, you know, just the inside of v. We don't want to modify the boundary conditions at any moment. That's off limits. The boundary conditions are sacred. They are boundary conditions because they do not depend on time. So that means they stay the same all throughout. So you only update the inside of your data structure, not the outside of your data structure. The inside of your data structure, everything that is inside of the boundaries, that does not include the boundaries. Everything that excludes the boundaries, right? You're going to update that into, well, what's the formula? Ignore the pressure. Come up with this guy. Minus what? UN, right? UN, obviously. Dimensions must match. Your dimensions must match. Otherwise, your code is not going to work. And obviously, you want this because UN times a forward difference, because that's how we decided to do it. Could have been a center difference, right? Or a backward difference, I guess. Technically, that will also work. Forward difference. Yeah, of what? Of u, right? Oh, but with respect to x. Oops. With respect to x, be very careful with that. That's for a match, as it's supposed to match, n minus 1 times forward if with respect to y, u. So we have this term here. Now, plus what? Plus the viscosity. This is going to be a very long line of code. A very long line of code. So Numpy, thank God for Numpy. For Python, sorry. In Python, you can do this. You just start with a parenthesis right over there, right? You cannot add things just like this. Plus nu, the viscosity, right? Nu times, what is this guy? Oops. Oh. This is the Laplacian of the function u in this case, right? We can also make a function for that, Laplacian of f. The Laplacian of f must be equal to, the Laplacian of f must be equal to, well, the sum of the second differences, right? The sum of this guy plus, right? The sum of the second differences with respect to all the directions. So Laplacian of UN, oh my god, are you looking what I'm doing? UN, obviously this is all UN, UN everywhere. Except here, right, because the formula is being here, right? But obviously this is like at the temporal step n, right? Okay, so we have the parentheses ready. Let's clean this a little. I guess I would like to, I don't know, I like it this way, right? This big parenthesis is what we have here, but without the pressure term. We're just ignoring that. Our function is called velocity without the pressure, conveniently. So now you multiply that by dt plus un, right? Un, with the dimensions matching, obviously. There we go. Ah, wait, this is so funny. Obviously, I meant here u. I'm so sorry, this was confusing. This is u. This is the formula for u. And I'm going to do a big blatant copy and paste here because, for v it doesn't change a lot. This stays the same really, like these guys here, because these guys are like these guys here, right? So that is just the same way. But what the functions are taking now is Vn. And obviously this guy that is adding up here is also Vn, right? This guy. Alright, I guess that should work. I really think that should work. I really hope that works. UV, I return UV. Nice. Amazing function. I love it. Don't look at anything that is over there, right? Nothing over there matters. But what about the pressure term? U star the predictor step. Oh, we are not calling our stuff that way. We're calling it the velocity without the pressure because that's what it is. This is the value of the velocity without the influence of the pressure. No joke, Einstein, we call it that way. Velocity without pressure. How do we solve the pressure Poisson equation? The pressure Poisson equation. You know, we're going to be attaching a screencast for this derivation of this guy, I guess. But you gotta trust Owkes that this is the pressure Poisson equation, except it's actually this one below. There was a typo, and we're sure of that. There was a typo in Owkes. This should be a positive sign. So trust us, this is the pressure Poisson equation defined in terms of the velocity with U star without the influence of the pressure. That's what a U star is. In a way this is returning U star, right? In a very important way. It's returning the velocity without the influence of the pressure. Oh wait. Is this really U? Wait, yeah, I think this is going to work because I'm wondering if, just to be safe, I think just to be really safe, like, well, U without pressure. It's like the next velocity without the pressure, really. V.copy, right? Just to be absolutely safe, I don't know if I need to save the values of the velocity. Well, when I solve the pressure Poisson equation, I use U star, but when I update V, I use U star, but I don't use U. Oh, no, wait, this should work. Yeah, I don't need to do this. Yeah. We update the velocity like progressively, every once in a while with new information, right? So it's like an ongoing process of updating the velocity. But the velocity beyond this step does not seem to depend on itself. So like, with UN, we can forget about it in a certain way, to put it away, because in the further steps, the pressure depends on U star, or U without the pressure, without the influence of pressure, and then the corrector step depends on U star and the pressure, but not UN, to put it that way, right? So yeah, this should work. Right. Okay. Now we have what? Well, obviously we forgot about the pressure, but just for a moment, we need to solve the pressure, and we do that with the pressure Poisson equation, which is this. Just accept this. And we break down the pressure Poisson equation to figure out what we can do with it, right? This is how the pressure Poisson equation looks if you break it down. You know how to calculate this guy. This is just the divergence of U star, velocity star, right? The velocity without the influence of the pressure, which you have here. But you need the divergence of these two guys, right? The divergence of these two guys, which is the sum of the first order differences, right? Of the finite difference approximations. Nothing out of this world, multiplied by the density divided by delta t. So this guy is really easy to calculate. In fact, let's do it. Right hand side, pressure Poisson. We're going to define a function. Def, right hand side, pressure Poisson. Except this is a horrible name, so let's not use this name. Let's not also use V, let's use R, get R. Why? Because that's what Owkes does, R. What is R? R is the right hand side of the pressure Poisson equation. Without the typo. This is a typo, believe it. Couldn't kill it. It's a typo. This is the right thing. And this is right, obviously. Right, this is R, so get R to get the right hand side, the pressure Poisson equation. Divergence, Bell, star. Bell star because it's this guy, Bell without pressure. Right, It's equal to nothing more than forward diff x of U plus forward diff y of V. Right. It's just what we have here times rho and delta t, right? So yeah. Well, this obviously I'm not sure if this helps to call this V without pressure. I know it's like a cumbersome name. I'm just having fun with changing things a little bit to emphasize different concepts. Right? U without pressure, and we return rho divided by delta t times the variance velocity without pressure. No, easy stuff. Why didn't I make a function for that? Well, I guess I could, right? Divergence, this would be like that, right? Except that it wouldn't. You take a closer look. There's an issue here, obviously. FG, I guess, right? FG. It's we're talking about a vector values function, right? So it's not really the divergence of f, right? No, like this will be the divergence of scalar value function to the multivariable function, right? But we don't want that. We want something more like, I guess, the divergence of vector value function, right? Vector value to the multivariable function, right? You know, I guess we could do something like this, right? 0 we could save f1, f2, I guess, or assume, right, it's a vector value function to put it that way, so we're going to say f1, you know, right? If not, you validate this, right? Like if it's not a tuple, then screw it, right? So I guess the way we will do this is like you put up a tuple in it, I guess. UV, right? Just put it in a parenthesis and use divergence vector value function, right? I guess you could do it this way. In the guide, I didn't do that because I think sometimes it's more readable to just, you know, go straight into it, right? Like, you know, the divergence vector value gets a tuple as an input. You know, for pedagogical purposes, sometimes it's just better to be explicit about it. So that's why in the guide we did this, right? And obviously it's kind of like somewhat nonsense to, you know, define this inside of this function, but for pedagogical purposes we're doing it. So we're like just putting this up here, just such that we're emphasizing how we are using it for pedagogical purposes, you know, really for the sake of pedagogical purposes, because obviously you will want to put these functions like here, but we're having fun. It's just a video tutorial. Okay, so the divergence vector value function, right? So rho dt. So we have the right hand side of the pressure Poisson equation. Now we want Pn plus 1. So we break that down, which is what Barba did, you know? They said, okay, let's say B is the source term. In this case, we call that R. That's the source term. It's the pressure Poisson equation, which means something different for us because Barba does not use a predictor step or corrector step or all of that stuff from Owkes. So it means something different for her, but that does not matter for us too much because we only took what we needed, what we wanted, which is have the pressure Poisson equation with the right hand side. So how do we arrive at a formula for this guy? That's what we want. You know, well, here's how we do it. In case you want to take a look at the algebra. You arrive at this guy, right? At this guy with this term here for the source term, right? So if we know that, which is all we need to know, how do I, yeah, so like want to just I'm going to delete this just for a second, lol. It's too distracting. So I'm doing the video tutorial like I don't want. Okay, so this is our formula, so we need to call that up. That's pretty much it. There's nothing different about it, I think. Well, you know, there's something I want to emphasize here, though. What's the dimension of this? You know, perhaps we want to say R is np zeros, you know, and y and x, you know. Perhaps we want to say that just so that we're at all times on the same page, that you know what this is going to return, because you know we're using these forward differences. You know, this is going to return something with a dimension that is obviously like just the inside of the grid, you know, like, right? So this is going to return something that is like of a shorter dimension than, you know, like the whole domain, the grid away. So perhaps this way of pulling it up emphasizes that, and it's useful. It's going to be useful such that we don't get confused, which is not how exactly we did it in the guide, but we explained that here. You know, but I'm going to do it like this because as I'm pulling it up on live, I feel like this might actually convey the intent of the code better at every step. So, right, you know, just keep things consistent. Okay, I know how to use them later, right, when you access them. And because this is related, I'm going to call, actually, you know, get P, get pressure, right, or solve Poisson. You might call it like solve pressure Poisson, right? And what does this take? This takes just R, I think. Well, let's take a look. The pressure Poisson equation, you know, once we broke it down and solved for the term that we want, really just takes, well, you know, P, you know, P at any moment, assume it's Pn plus 1, P at the temporal step, next temporal step. We never care about the P at the very, very first temporal step in a certain way. We do kind of, how do I explain that? Even the data structure that we have here, this P from the very beginning is like P at the next temporal step, you know? This is U at temporal step n at any moment. This is P at temporal step n plus 1 at any moment. Even the very first values, really. So that's what this is taking. It's P at the next temporal step, which is what we have here. It takes the right hand side, which we call R here just for fun. Sorry. Just that, really. It's really just that, P and R. But there are three main terms, you know, so we're going to break it down that way, right? Term 1, it's, we can see just right there, it's dy squared, p I minus 1, j. But, well, the I is to put them that way. Those guys are like, you know, here, right? Like it's so. Zero minus 2. Just a small, yeah, this is 0 minus 2. Sorry, small notch. Okay, 0 minus 2. Sorry, I should not cheat really. This is, you know, I wonder if I can copy and paste that. Oh wow, look at that comment. Nice. Very useful. Well, I can actually copy. I didn't know that could happen. It could. I like the format of that comment. Nice. Oh wow, look at that. Yeah, that's useful. Yeah. Like that. Term 2 equals this guy. This guy. Okay, there you go. I can put that up very quickly. 0 minus 2. Everything that is inside the grid. Okay. Term 3. Term 3 minus R. Well, we call it R, right? You know? Now it's R. Rn. R. You know, I know that in the guide we just refer to it like this way. Oh, I didn't copy this very well. Like this, right? Dx, right? Dy squared, right? In the guide, we refer to this like this without the indexation of R, because in the guide, I'm sure like I did it like this, right? I knew I was doing it that way, so I knew how to use it, right? But right now we're using it this way, so we know that R is like a data structure that has the same dimensions as like the whole grid, to put it that way, right? So we need to access just what we must use, you know, at every moment. Just what is inside, really. But because what is R in the end of the day, it's like something that comes from this, right? You cannot have values for these rates of change like at the boundaries. This gives you an object that is really contained inside of the boundaries, right? Of the discretized domain, right? So, right, you know, everything at any moment is kept between the boundaries of the discretized domain. So R should too, right? So that's what we do here. There are only boundaries conditions for, properly speaking, for, I believe, for the logic. Okay, so P equals, and I believe, well, yeah, it's just this, right? Should we just place P equals to, oh, by the way, obviously, pressure, well, the sum of the terms, right? Yeah. UI. Right. That should be it. Yeah. That should be it. That should be it. Now we have the pressure, the functions for getting the pressure, getting R. Well, we still need a function for updating the velocity. That's what we're doing. Update velocity. From whatever we have, right? But I would like to have a sense already of how we're going to use this, right? Simulate cavity flow. For NT, n equals to, well, I wonder if, well, what's the first function that I need, right? Velocity without pressure, right? And this returns like U without pressure. U without pressure, V without pressure. And then guitar. Just like that. And then UV. No, wait. P should be equal to emphasize that, right? And then update velocity, which takes U without pressure and P. I think. Well, let's take a look at the corrector step though. Formula for the corrector step. Well, that depends only on U star and the pressure, right? The gradient of the pressure. Yeah. The velocity is without pressure and the pressure, obviously, yeah. Update velocity. Right. Technically, for the way I coded this up, like as I said before, I sort of like made a comment on this. The velocity beyond this point, whatever is coded in here, sort of like does not depend on the original UNVM values, like you got copy, copy. Like this could be very professional in many ways, but you don't need this. I'm sure this will work really well. Like you could just just sort of like think that you're updating the velocity progressively. Obviously, these variables are changing, this UV, but that's okay. It's just like the inside, right? That is changing. Oh, by the way, yeah, obviously, This is super important though, if you're going to do it this way. Oh no, I'm sure it returns like a whole object, right? You know, a whole object. No, this is okay. Yeah. This should work, I think. Yeah. You know, if you needed these values like later, because for whatever reason the corrector step was defined in terms of like un and not just u star, right? Like if this un was defined here in the corrector step, like you will need to like do it like this, right? Obviously. But that's not the case. So you can sort of like progressively update everything. That's one way to think about it. Yeah, I think this should work and return UVP. Oops, P. This should work really well. Even here, I think that in the guide, I saw it quickly a moment ago. I think I did something like this. I can imagine a lot of formulas or mathematical models and situations in which like this might be useful, but not here, no, because if you look here, there's no risk of affecting P, so you don't need to create a copy of that variable at any moment. You don't need to. And technically, because you're inserting this guy, which I'm not sure if it says a global variable, assuming it's local for whatever reason, well, return it, right? Always return it. Yeah, to update it properly to make sure that you're updating the actual value, not just losing it here. Yeah, and this obviously will work. So update velocity. The corrector step, this one, you move this guy here and plus the starter velocity, right? But I'm sure that I have it like conveniently broken down here, right? Beautiful. This thing here obviously is a vector equation, so breaks into this. Okay. U is going to be now equal to minus dt rho, the density, multiplied by let's do a forward difference. It's a first order difference, that's all that matters. Forward difference of P plus guys, I really think this works. But now I'm hesitating that it's going to work. Like, holy cow. Wow, what was that the right way to think about it? Now I'm getting confused. Because these are vectorized operations. I don't know. You know, just to be safe, obviously, and perhaps this is actually better. You know, obviously this also looks like this conveys the intent of the code better, right? Right? This is how we should do it. At every moment we take decisions. Right, this is a partial with respect to y, right? X and y. The boundary conditions are preserved in these UV objects, right? Because, you know, we're passing them from the source. So, UV. Okay. Is it going to work? Pressure UV. Yeah, it should work perfectly. We're going to perhaps call it always another step, right? Now I think we can run this. Well, first of all, like you need an nt value, right? Remember that I told you that you could define this as a global variable? Well, let's not do that. Let's actually assume it's something like a value that, you know, you would use here, like on the go, right? Right, 100, that sounds about right. UV are now global variables. We're thinking about them that way, which means that you have to sort of like restart everything every time that you want to like test your simulation again. P is also a global variable, so this should be the most minimalist way to call this, I guess. Wrong. Oh, restart the wrong. Int object is not callable. Oh, what did I do here? Referenced before assignment. Oh, it's taking them as local variables. Why? Huh, that's interesting. I would have hoped that it would interpret this as global variables. They would know where to find them, but apparently it does not. I'm a little surprised about that. Yeah, I don't know why. Interesting. Maybe because it's inside a folder. The scope should have been global. Yeah. Wow. I know that in a lot of programming languages, the scope of those variables should have been global, like really global. I wonder if it's a nuance of Jupyter Notebook or Python. V without pressure and P, update velocity. Oh yeah, well, I guess that, well, there's always the right way to do things, always, right? You know, perhaps this conveys the intent of the code better, right? You know, we have UN, VN. Then we have the U without pressure and the V without pressure. So let's not do it this way. Then have this guy. But I really don't think that I need this, so let's keep it this way, okay? Oh my god, I don't want to confuse you too much. Wait, what happened here? No. this gets me a version of the velocities without pressure that I use here, so that's correct. Update velocity needs the velocity without pressure, but it also sort of like benefits from well, this may look horrible. I think this would work. Well, okay, this might really look ugly. Right. I think this will work with like obviously this is not the intent of the code. Oh my god. How to express the intent of the code? I guess this is really the right way to think about it. I mean, yeah, then without pressure, yeah. I guess I feel like, what's the right programming for when you in practice? Like, I know how to make this work, just this returns Q without pressure, V without pressure. You know, let's be hyper explicit, just such that at any given point, we don't lose the intent of the code. Okay, perhaps this is the right way to do it. You know, like it's not just about making things work. It's about conveying the intent of the code. I think like at every step. So this returns that, right? This function, scale with pressure, returns this, right? And I guess, ironically though, sort of don't need that. This could be just B. Well, no, perhaps this conveys the intent of the code better, right? Bien. No? This looks nicer and conveys the intent of the code really well, I think. It's funny, actually, you end up needing like it's a different way to put it. Yeah. This conveys the intent of the code much better. We have R, get pressure, this is fine. Alright. Okay, pressure. Let's get rid of this. This is how we're going to do it. It's much better. Yeah, this should work. Oh, why? Oh, look. Okay, velocity. Yeah, I always do this. I had this trouble before. Well, this is type of thing. When I had this problem was because there was a sign, the typo in Owkes. I was sure it was a typo. Oh, we don't have boundary conditions for the pressure. Yeah. I haven't explained the boundary conditions for the pressure. We're just going to sort of like steal them from the guide. They're sort of like explained there anyways. So maybe that's why. Oh, we're having an issue somewhere. Just let me check the signs for R. Is this supposed to be minus? I don't think so. Doesn't seem to be related to that. Well, I don't think that's what's going on. So I don't know. I messed up function. You know, double thinking. Maybe this was a good idea. I know that works conceptually, but maybe no, this is the Y one, right? Okay. For feeling, maybe that, I don't know why. Maybe not. I don't think it has anything to do with forward differences, but just I mean, I'm going to, for a moment, use the definition of a center difference, just such that I figure out what might be troubling us here. Oh, it worked. Okay. That doesn't probably look well to the audience. Why is it that it's working with the center difference? This is such an irony because Professor Lorena Barba uses forward differences. So I don't see why it wouldn't work well here. What's going on? Forward differences, backward differences, right? I mean, they use forward differences, so why our forward differences will not be working? Well, let's visualize just to make sure. You know, visualization is a little like out of the scope of this tutorial. So I'm just gonna make sure that things sort of work. Oh, we don't have the meshgrid. Oh. Well, kind of do. We already, well, in a way we already sort of like talked a little about visualization. Yeah, that sort of looks okay, I think. Yeah, it's working. You know, it looks kind of like, as I said here, right? You know, it's hard to imagine why that would be the movement of the flow, right? If you have that velocity going rightwards, the top. Yeah, so that's the tutorial, but I really want to like figure out really quickly, or at least try, why our forward differences are not working. Oh, let's try forward difference. I don't know. This is probably a weird combination. Doesn't work. Why? Should work. Very quickly, let's figure it out. I'm even going to try the backward differences. Not working. Forward differences do not seem to work. What about backward differences? Confused. Oh my god, wait, let me delete that because for a moment I just got confused. This is the backward difference for x, so we paste it here, and this is the backward difference for y, so we paste it here. I'm obviously just making this quick change on the function that I know all of the code is using, just to test. Backward and forward differences don't work. Why? This is such an irony because Lorena Barba says forward differences in their vectorized operations. Huh. Oh, good test challenge. I wonder if it has anything to do with, like, here we sort of like ask that question. I kind of think that the answer to this question is yes, it can break, but it would break for this and just maybe, but we're not using Neumann boundary conditions here. Like in the case of the velocity, forward, backward, center differences, yeah, that has an impact on, that would have an impact on Neumann boundary conditions, right? If the velocity boundary conditions were Neumann, right? Because we're taking derivatives of the velocity all the time in the code. But for the pressure, if you think about it, we are safe. We switch. I thought we should be safe between switching between forward, backward, or center differences, because for the pressure, we do not take forward differences. Do we? Or oh no, wait, maybe we do. Ah, yeah, we do take forward. We do take with approximations the pressure. Oh, so maybe that's why. But if Lorena Barba used... Oh, I have a theory. I have a crazy theory. I believe that... No, wait. Let's bring the center differences. Like, let's just bring them, but let's just use them in one single place, just to isolate the problem, right? Maybe the problem is there, right? We don't need to do it exactly the same way. I have a feeling that maybe just for the pressure, which uses Neumann boundary conditions, maybe just there we need to use center differences. And maybe Lorena Barba did that and I didn't notice. And perhaps just with the velocity we're fine. Oh, look at that! That's an amazing way to close the video tutorial. Huh. Oh, yeah, look at that. Then I didn't notice that. Yeah, I'm sure that Lorena Barba, their implementation, well, they solve the pressure completely different. So I guess it doesn't matter. No, but you know, here, for example, I think we see the pressure. This looks like a center difference, I think. But I'm not sure. I mean, yeah, because it's like one forward and one backward. But we don't see if this is being divided by 2x or something, 2dx or something like that. But maybe this came from the approximation of a center difference for the pressure somewhere. Yeah, look at this. Yeah, this looks like a, yeah, here. Yeah, this looks like a center difference for the pressure. One forward and one backward, 2 delta x. One forward and one backward, vertical direction dimension, 2yx. 2 delta x, sorry. 2 delta x. No, 2 delta y, obviously. Here's a 2 delta y. So he's, and you know now exactly why a center difference. Well, you can grab a piece of pencil and paper and sheet of paper and start like figuring out why exactly the Neumann boundary conditions of the pressure like will break, and see it for yourself. But the concept here is that for Neumann boundary conditions, if you're going to define them this way in the discretization, which is essentially saying, okay, the rate of change, I want it to be 0 in the boundaries, in the foremost boundary or farthest boundary in the horizontal dimension. So what I'm going to do, I'm going to say like the last guy is the same as the previous guy, right? So that's sort of the idea. The guy that is previous to the last guy, right? That's sort of like the idea. When I read this, my first thought is that this looks like defined for forward differences, right? And that would have been my first thought, but you know, the important concept is that for Neumann boundary conditions, it does matter how you are approximating the derivatives, obviously. It's not exactly the same, because you are making assumptions about how the rates of change are being calculated by sort of like setting these equalities here, right? Finding this stuff here. So it's not surprise that, you know, it seems suspicious that maybe for the pressure, if we were approximating derivatives for the pressure anywhere, then that can be tricky if we would switch all of the sudden from center differences to forward differences or any other type of difference, whatever. Yeah. Okay. Yeah. This is so cool. I'm so glad we coded this up. We had this struggle. I think we learned something about Neumann boundary conditions. I mean, even I sort of like figured something out. Okay. 2 hours and 20 minutes. I think it's kind of a nice crash course. It's going to be an optional reading. I recommend doing something similar, following along this, trying to play with the code and make the most of all of the resources. Yeah, good luck. Let us know if you have any questions. Bye. Cheers.